Start? Okay. Guys, welcome to class and thanks all for turning up. As you guys received a preview email from me earlier, we're going to be talking about lower bounds or complexity theory for optimization, right? First, definitely probably the most important question is why bother about lower bounds? And the answer is often similar to the answer given in CS theory, and we'll talk about that. Then I'll go into a little bit of the formalization, talking about oracles. What do I mean by I get zeroth order information or first order information or second order information? And what do I mean by a stochastic or a non-stochastic oracle? Third, we'll look into the role of the geometry of the set that you're optimizing over. So if the optimum rate at which you can optimize will often depend on whether this is an L2 ball, L infinity ball, L1 ball, and so on, and what your function's geometry is like, and so on. And so we'll look into why geometry plays a role, and then we'll go into lots of examples of lower bounds and what they should tell you, like how do you read the statement of that lower bound and what you should take away from that. And we look at lots of exceptions to, I mean they're not really exceptions, but you might believe that it seems to be violating a lower bound, but you'll often see that there are special cases which you can solve much faster than what the lower bounds tell you. And a lot of these exceptions are classical from the 80s, and a lot of them are just from 1 year ago. And so we'll look into some caution and cautionary tales when studying lower bounds. Okay, any questions? Okay, so maybe let's start with the why bother question. Do any of you have any feel of why people study complexity theory or lower bounds for either CS or for statistics or for optimization? And can you offer any thoughts as to why this is important? Yep.
Basically, to know whether it's possible to enhance a given complexity of a method.
Possible to enhance the complexity of a method. Okay, so can we do better than say gradient descent or something like that? So we have some method that we like to use, and we'd like to know, can we actually do better than that method? Okay, that's a good reason to study these bounds. Any other ideas? Yep.
Well, you can always get empirical results on a method, but sometimes it's nice to have guarantees about how it's going to do in all cases.
Okay. Does the theory match practice? Maybe something like that. Okay. Any others?
Understand the worst case.
Yeah, understand the worst case. That's right. Okay, that's a good one. So what's the worst case for this function? So what's the worst case? Right. So you might actually in practice see that it's performing well on the examples that you tried, but if we want to really understand what the worst case is, then understanding lower bounds is good, because you're basically looking at the worst case performance, right? Anything else? I mean, I don't have any other reasons, but those were good, all good reasons. Yeah, so basically, like when people started to study gradient methods or subgradient methods and all of these problems, this was in the 50s and 60s that people started to study these methods, and then they started proving rates as to how well they do in general. And you started to get all kinds of rates. So people got rates that looked like, after t iterations, my function error will look like 1 by root t. I'll formalize this, what I mean by that later on. And then for some other example, it turned out to be 1 by t. And then it turns out you try Newton methods, and then it looks like e to the minus t. And then you do something else and you get another rate, and you have no idea. You get all these rates and you have no idea what rate's the right rate, what rate should I expect to get. Should I expect, this is called linear convergence or exponential convergence. This is like 1 by t, 1 by root t. I have no idea what to expect. I mean, I try it out, I seem to get some rate. I have no idea, can I get any faster? Is this the right rate? No clue. Did I just implement it wrongly or something like that? So people started to get these bunch of rates, and so then people asked, okay, let's try and establish lower bounds, which would tell me something like there is no algorithm that can do better than this rate under some assumptions. And maybe so for convex functions, if they're not differentiable, then you can't get better than that rate. For strongly convex functions, if there's noise added, then you can't get faster than that rate. So basically trying to understand under what situations, under what function classes, you can get what kind of error rates. And I mean, I'll formalize what I mean by an error rate, but broadly that's just to answer those kind of questions, to get rid of this uncertainty of can I do any better. That's why people started to study lower bounds. And that's why we look at them too. Any questions? Okay. So let me go on to formalize the different settings in which people study these kind of things. And the first thing that matters a lot is called what's the oracle model. So in the oracle model, it's also called the black box model. You don't know anything about your function, and there is a guy, let's say Dumbledore, who knows the function, and you only get to ask Dumbledore queries about this function. Okay, and Dumbledore gives you very specific kind of information. Okay, so you have the 0th order oracle, in which all you get to do is, you get to ask for a point x in your domain, and what Dumbledore gives you is only f of x. So this is called 0th order information. It's called 0th order for a reason, and the reason is that a first order oracle would be when you get to query x at any x in your domain, and Dumbledore gives you f of x, and he gives you g of x, which is the function value and the gradient value at that point. Okay, and then there's second order oracle, in which you query at a point x, and you get the function value, you get the gradient value, and you get the Hessian, right? And you could go on, but typically nobody really wants to study beyond second order information, right? So, and people study these oracles basically because if you're optimizing any function, often the two most time-consuming tasks are evaluating the value of the function or evaluating the value of the gradient of the function. And you want to know what are the minimum number of times that I can query the oracle, which is what is the minimum number of times I need to calculate the gradient value in order to actually optimize my function. So for example, I mean, you'll often look at functions of the form, this is classical in machine learning. So you have some empirical loss, you have n data points. This is some loss function like the hinge loss, logistic loss, regularized squared loss, anything like that. And you have an unknown weight vector, and you want to minimize this. So you have something like this, maybe with the regularization. You can absorb the regularization inside if you want. And you can clearly see that if you wanted to evaluate the function at any w, you have to go through all of your data to evaluate that function. So that's like really expensive. Just asking for a function value is very time consuming. And similarly, like asking for a gradient is, again, calculating the gradient for any of these guys and summing over all your data points. So asking for a gradient at any w is really expensive. So you don't really typically want to do it. This is this is what's going to take up most of your computation time, just finding the function value or finding the gradient value. And so you basically want to ask what is the minimum number of queries to the oracle I can make, which is, in other words, what is the minimum number of times I calculate the function value or calculate the gradient value for which I can optimize my function. So these, what I've described right now, are what's called deterministic oracles. That is, I actually give you the real function value. Okay, and correspondingly to these, you have what are called stochastic oracles. So this is non-stochastic. And a stochastic oracle is in which a 0th order stochastic oracle is one in which you get f hat of x, which is just an unbiased estimator of f of x. Okay, so you get something like that. So this is what he tells you. So there are several ways of thinking about this. You can either think that he actually gets f of x, but then he corrupts it with Gaussian noise and he gives it back to you. So he gives you f of x plus 0 mean Gaussian noise. So in expectation, it's still f of x, but it's noisy. Another way of thinking about that is, say, in this setting where when you want f of x, what he does is he just evaluates it on a random data point. So he just evaluates it at a single I, and he gives you back Li of w. Okay. Now clearly that Li of w is unbiased in expectation, because the expected value of Li of w is exactly this quantity, and so what he's given you is an unbiased estimator of your function. So that's the stochastic model. We'll see later on that this is a kind of special case of the stochastic model that has better algorithms to solve it. But in general, you should just think of, you don't know anything else about what he's given back to you, except that it's an unbiased estimator of the true function value. And similarly over here, you get back f hat of x and g hat of x. Yep.
Is the unbiasedness always important? Is that
yes. So as far as I know, yeah, you want it to be unbiased, right? So you can analyze things in which the gradient has an error which is not unbiased, and then you can calculate rates in that setting too. But I guess it's most typical to look at an unbiased error, just because it's also easiest to obtain. Similarly, if I wanted to give you an unbiased estimate of the gradient, instead of calculating the entire gradient, I'll just take a random data point, calculate gradient of Li of Wt at that point, and I'll return that to you. And this is an unbiased estimator of the gradient of this. And so g hat in expectation is g. But I'm giving you something that's noisy. It's not really the true gradient. So this is called the stochastic model, right? So the stochastic first order model, the stochastic zeroth order model, and similarly you have the non-stochastic zeroth order, non-stochastic first order. This is just trying to tell you, do I have noise and do I have gradient information or not, right? So those are the different kinds of oracles that we'll deal with. Okay, there are actually other kinds of oracles. For example, there is a zeroth order comparison oracle. Okay. So what the zeroth order comparison oracle does is you give it 2 points x and y, and then it'll give you like a +1 if f of x is greater than f of y, and it'll give you a -1 if f of x is less than f of y. Okay. Otherwise, so again, this would be noiseless. If this was noiseless, then you always get +1 if it's greater, and you always get -1 if it's lesser. If it's stochastic, then you'll get this with a high probability, and you'll get this with a high probability, but there's some probability that there'll be a sign flip. Okay, so that's called the comparison. So you can, I mean, this might be relevant in cases where the only kind of queries you can make maybe to a user are, do you like this more or this more? And then he just says, I like, maybe there's no actual function value he returns, but he can compare easily between two function values, but he can't actually return a number. So he can't tell you how much he likes the beer, like 8.5 doesn't mean anything, but he can tell you that he likes this beer more than that beer, right? So you can imagine cases where the zeroth order comparison oracle might make sense. But at least for now, for this class, at least we'll just talk about these kind of oracles, and especially the first order oracles. There is literature on this, and I can point you to that, but we typically deal with first order methods, which are like gradient based methods, and that's because calculating, often in problems that we deal with, calculating the gradient and calculating the function have similar kinds of complexity. So we don't mind spending this. I mean, if you're going to calculate a function, we might as well calculate a gradient, because we still have to sum through all the data points. And similarly, if I'm calculating an unbiased estimate of the function, I might as well calculate an unbiased estimate of the gradient. So typically, people do first order methods because it's not too hard to get first order information, but it might be too hard to get second order information, which is a Hessian, which is an entire matrix that you have to calculate and stuff. So it might be a little harder. So that's why in this class at least, we'll talk about basically the first order setting. Any questions? Okay, let me move to that side. Okay, so let's kind of formalize what our aim is. Okay, and our aim is going to be in terms of error, can be thought of in two different ways. One is given an epsilon, you can think of this as 0.01 or something like that. I want to find an x such that f of x t minus f of x star is at most epsilon. So I say x star is my optimum of the function on the domain I'm dealing with, and xt is my function, is my iterate after t steps of doing whatever optimization algorithm. But my aim is to try and find an xt such that f of xt minus f of x star is at most epsilon. Okay, if this was a stochastic method and there was randomness involved in getting the gradients, then maybe what I want to do is actually, in expectation, I would like my f of xt minus f of x star to be at most epsilon. And this expectation is over the randomness of the oracle who gave you back the noisy estimates. It could also be over the randomness of the algorithm. So your algorithm could also use randomization in some fashion, and that's fine. So this is called function error. But alternately, maybe you don't care about the function error. Perhaps you care about the point error, which is you want xt minus x star to be at most epsilon. Okay, so this is called, and I call this function error, I call this point error. So you could be interested in either of those. And the way you would, there are two ways in which you could state your aim. Okay, so you could state your aim in two ways. You could either say that I have a budget of t queries to the oracle. What is the smallest epsilon I can get? So what is the smallest epsilon I can get in t queries? Or I could reverse this question and say I have a target epsilon. I have a target epsilon, and what is the minimum? What's the minimum number of steps I will need to get to that target epsilon? So these are just inverse ways to say the same thing. Either I can say you have t steps, what's the best accuracy? Or I have a fixed accuracy, what's the minimum number of steps you need to get to that accuracy? And they're literally inverses of one another. For example, what I stated over there, for example, the 1 by root t, 1 by t, those were in terms of this, that is, so this is at most 1 by root t. So, and what I mean by this, maybe I should say epsilon f. So the function error is at most 1 by root t. If I make a statement like this, it is kind of equivalent to saying that t is basically greater than this. So I can just reverse the inequality, right? So either I say that at most in t time steps, I can expect an epsilon of like 1 by root t, or if I want an epsilon, then I need at least like 1 by epsilon square steps for me to get an accuracy of epsilon. Okay, so do we get these two basically equivalent ways of stating? Yeah, sorry. Yeah. Okay. So this is our aim, and we're going to ask what is the, in either of these ways of stating it, and I'm going to try to stick to this way of stating it, which is I give you t time steps, t iterations, 10,000 iterations. What is the best accuracy you can get me, right? Is that clear? Any questions? Okay, so I think it should kind of be clear why the geometry of the set matters, but I'm going to ask you to try and guess. Can you guess what's the difference between optimizing over the L2 ball, right, which is say x minus, so say x2 norm is at most r, versus the L infinity ball, which is x infinity norm is at most R versus say the L1 ball. Okay, so what's the difference between optimizing in all of these, and why is there a difference? Yep. Sorry?
It should be greater than equal to the second one. Is the t is greater than equal to 1? Actually, my interest is. Suppose you want like 0 error, you need like infinite.
Okay, so I mean, if you could do that too. That is, your error will be at least 1 by root t, or t will be at least 1 by epsilon square. Any questions? Yeah, so why is there a difference between optimizing these over these? Any ideas?
Projection.
The projection operator is different, but that's the algorithm. So in terms of rates, that is how difficult it is or how hard it is to optimize over these sets. Why should it be easier to optimize over one set or another? So L1, so the smoothness of the set, maybe, so that could play a role, how smooth the set is, how easy it is maybe to represent the set.
Size of the set.
Yeah, size of the set. So what do we know about the size of the sets?
L1 is smaller than L1.
Okay, so basically, as Viru said, the size of these sets is completely different, right? So if I look at the corners of this set and I calculate the diameter of these sets, then they're all completely different. The diameter of this set is R. I mean, the L2 diameter of this set is R. But this guy has corners. Its corners are R in each dimension. And so its diameter is actually like R root D. So in some sense, it's actually a much larger set. And similarly, this will actually be like R by root D or something like that. Or maybe this will also be R. But basically, this is a much larger set, so you're going to take more time to find the minimum if the minimum is in this set. Right? If I give you an extremely large set, you're going to take more time to explore that set to try and find where the minimum is. But you should see that all norms are basically equal to each other up to a dimension factor. So the only difference that this will make in all the rates is in the dimensionality that you're working in. Okay, so it's not going to make much of a difference in terms of time. Okay, so your t dependence will be the same, but your d dependence is basically what's going to change with the geometry of the set. And that matters a lot because, I mean, especially in machine learning when we're dealing with high dimensions, you really want to bother about that root d factor, because if you're dealing in 100,000 variables or something like that, that's 1,000 times difference that you're looking at. And we'll actually see that algorithms do have this guarantee. They have different guarantees with different dimensionality, and I'll give you an example of that later.
I think the confusion of like greater than or equal, less than or equal is because you're making a worst case statement, not a universal statement.
Yeah. So in the worst case, this statement is true. Right.
Will give you this.
Yeah. So lower bounds would be stated in this fashion. That is, if I give you a t, then there exists a function for whose function error will be at least 1 by root t. And if I give you an epsilon, then there will be a function for which you will take at least 1 by epsilon squared steps so the lower bounds will be stated in this fashion, upper bounds will be stated in the reverse fashion. Any questions? So another place actually that the dimensionality comes in is in the function class that you're dealing with. So this is like kind of often glossed over, but it is important for the same reason that the set is important. You get dimension factors. So you often not assume also, but you do have things like f is f is Lipschitz. Okay. Does anyone remember the definition of f being Lipschitz? Yes.
F of x minus f of minus.
Okay. What is it? F of x minus f of y. Absolute value.
Less than or equal to L.
Less than or equal to L.
Norm x minus y.
Norm x minus y. Right? Okay. Anything, everyone agree with this? That this is what it means for f to be L Lipschitz? Anyone want to add anything to it?
You need to define the.
So you need to define the norm. So this is often like, I guess, the glossed over part, because f is Lipschitz in some norm. So that norm could be the 1 norm, and then in this case this would be 1. It could be the 2 norm, in which case this would be 2. Could be the infinity norm. So you actually have a function at hand, and it could be Lipschitz in different norms. And that really matters, because when you change between norms, you lose a dimension factor. So it really matters, the function that you have, is it naturally spherical, or is it naturally cubic in nature, like a cube or something like that. So it matters, like in infinity norm would be that, like, element wise, coordinate wise. So if your function for some reason is coordinate wise separable and behaves well on each coordinate, you might have it to be Lipschitz in the infinity norm. So it's like kind of, and the equivalent way of saying this is actually that the subgradient of f in the dual norm is at most L. So whatever norm I state this in, it's exactly equivalent to saying that every subgradient of f at any point x in the dual norm is bounded. You guys should have seen that in the other optimization course. Okay, so if I say it's bounded in the infinity norm here, this means that the L1 norm of the gradient is bounded. So, so this is another place where the geometry matters and you get dimension factors. Right? So I think in a very analogous fashion, people don't often say this, but when you say that f is strongly convex, okay, the statement of that is like f of y is at least f of x plus gradient of f times y minus x plus lambda by 2 times y minus x the whole squared. Okay, so you often write something like this, but really what you should be saying is f is strongly convex in some norm when you put that norm here. So if you could put a 1 here and a 1 here. For example, there is if you guys are familiar with the entropy function, then the entropy function is actually strongly convex with respect to the 1 norm. If you're used to the squared loss function, then the squared loss function is strongly convex with respect to the 2 norm, and so on. So different functions are strongly convex with respect to different norms. So you really want to take care about when you make these statements, just be a little bit more careful. And all of these will count in your statement of lower bounds, right? So you want it to be tight in dimension, in these constants, and so on. Any questions? Okay, so let's look at an example statement, and this is going to be our first example statement of a lower bound. Okay, so example, and this is going to be let's say some general f which is smooth or non-smooth, which I mean differentiable or not differentiable. So remember in the first order oracles, I told you I got an unbiased gradient. If the function was not differentiable, then you got any subgradient. Okay, so basically then there's an entire set of subgradients, and you got any subgradient at that point. If it's differentiable, you get the gradient. If it's not, you get any subgradient. Okay. So this is from a paper by Agarwal, Bartlett, Ravi Kumar, and Wainwright. So Bartlett and Wainwright are at Berkeley, Ravi Kumar is at Austin, Alex at MSR. So these guys had a paper a couple of years ago, and this is just adapted from their paper. Okay, so let's say F is convex and L Lipschitz with respect to the infinity norm. Okay, and let's call the class of all. There are lots of functions. There are lots of functions that are convex and L Lipschitz with respect to the infinity norm. Let's call that class of functions FL of S. Okay, where S is a convex set which is bounded in which has S is such that it contains B infinity R. So S is any convex set that contains the infinity norm ball of radius R. Okay, so basically the infinity norm is going to come into play for S and for F. Okay, and on this set S, F is convex and L Lipschitz with respect to the infinity norm. And let's call the set of all such, I'm going to call this, some kind of script S. Okay, so there are lots of sets which contain the infinity ball of radius R, and let's call the set of all such sets as script S. There are lots of functions which are L Lipschitz and convex on that set. Let's call the set of all those functions F. Let O be an oracle. Okay, and an oracle is basically, it's just a function that takes in x and it gives you f hat of x and g hat of x. Okay, so this is the stochastic setting. So you have a stochastic oracle, but there are many oracles that are of this form, and let maybe some script O be the set of all oracles. Like I could add Gaussian noise, or I could add Laplace noise, or I could add some other kind of noise. All of those would leave it unbiased, but they're all different kinds of oracles. And so let the set of all such oracles be O, and let O be any one oracle like that. Then, and let A be an algorithm, that queries the oracle t times, that has t queries to O on the set S. And this could be any such algorithm. This could be gradient descent, subgradient descent, accelerated gradient, whatever. Like whatever algorithm that you can think of and be super clever about. So let the set of all these algorithms be A. Okay, some script A. Okay. Now the statement is that, let me write it down first. The soup overall O in script O, the soup overall S in script S, the inf overall A in script A, the soup overall F in script in whatever FL of S. This is also A of S, right? And it gets T queries if you want, of expected value of f of x t minus f of x star f is at least L infinity R infinity root d by t. Oh, by root t, sorry, by root t. Okay, so I'll help you parse this, but let's just read it once more. It says the soup over all oracles, the soup over all sets, the inf over all algorithms, the soup over all functions of the expected error in the expected function error is at least that's the L infinity, that's L infinity times R infinity. Okay, this is what I mean by R infinity. Root d, which is the dimension, divided by root t, the number of queries I get. And what this means is that all you are in control of, which is the, either you can think of the optimizer or the learner or whatever, all you are in control of is this guy. You want to minimize the function error, but you want to you want a guarantee which doesn't depend on the function, like in the sense that you want an algorithm that is no matter what the function is, I can optimize it at a good rate, right? But you do get to see the set, and you don't really know the oracle, but in some sense these guys go first. Okay, so Dumbledore goes first and he chooses an oracle, and maybe he even tells you that this oracle is going to return the true value corrupted with Gaussian noise. Okay, so Dumbledore chooses an oracle and he tells you. Dumbledore chooses a set. Maybe he chooses the L2 ball or L infinity ball or whatever. He chooses some set. All the set has to be is that it has to contain, it has to be larger than the infinity ball of radius r. Okay, so he chooses any set and he tells you what the set is. Then you choose an algorithm. This algorithm knows the set, so it's going to make queries on the set, and it can make t such queries to the oracle. And then once you've chosen your algorithm, he says, okay, I'm going to show you that there is a function. I'm going to choose, Dumbledore gets to choose the worst case function. He gets to choose this. So this is Dumbledore and this is you. Okay, this is Dumbledore, this is Dumbledore. And he chooses the worst case function such that the expected error is at least this much. So he's guaranteeing that no matter what you do, no matter how intelligent you were and how well you designed your algorithm, you cannot guarantee an error of smaller than this. Because no matter what algorithm you pick, he can pick a function from the function class on which your error is at least this much. Okay? Any questions?
We can push R infinity always very small. Right?
Yeah, if R infinity is very small, then this bound is very small. That's all.
Yeah. So I'm confused that basically, so suppose S is like R to the power D.
Yeah, suppose, no, okay, S needs to be a bounded set, but anyway. Sure.
Okay, so suppose S,
So suppose it's R to the D also, that's fine. Suppose it's R to the D, and suppose you chose R infinity to be 1.
Yeah.
Then this is a valid lower bound, but it's a very weak lower bound. You could have chosen R infinity to be 2 also. You could have chosen it to be 3, right? Because if your true set is R to the D, or something like that, it's an unbounded set, then all of those R infinities are all valid lower bounds.
Yeah.
So you could have put them as 1, 2, 3, 4, 5, anything. They're all valid lower bounds. So basically, you don't have a lower bound, right? The lower bound is infinite in some sense. So if your set is bounded, then the best lower bound you can get is the largest R infinity that you could have fit inside that set.
and A can include an algorithm, even like an algorithm that remembers previous gradients.
Right. So A, yeah. So maybe, more formally, A is any algorithm that is a first order algorithm, which means that it starts at so what's a first order algorithm? Maybe I should write it here. So a first order algorithm is any algorithm that starts at x naught, and every iterate xt is in the span of all the gradients. So maybe g hat of x1 to g hat of xt minus 1, right? So basically, every iterate that it chooses has to be in the span of the gradients and x naught. So this is what you call a first order method. It only uses gradient information, doesn't calculate Hessians or anything like that. And so basically, yeah, A is any first order algorithm. Any questions?
So this doesn't include proximal gradient? No, because it's not in the span of.
Okay, so actually it does, but so this is usually used for smooth. Yeah, it's actually for smooth optimization. I think for non-smooth optimization, it's just, you just get to access T gradients and you can do anything you want with them.
You don't need to restrict your update.
Yeah, you don't need to. For non-smooth, you don't need to update, restrict your update to that, that's right. And I'll get to where proximal methods fit in.
But even for smooth algorithm, you can play some like tricks on the gradient.
Yeah, then you can't do better than the lower bounds I will talk about. I'll talk about deterministic smooth optimization. I'll talk about the lower bounds you get there, and I'll come to that. But the way to read this is, if I don't know anything more about my function, that is, I don't have strong convexity, and I just know that it's some convex non-smooth function, and I get noisy gradient values, then I cannot get better than a 1 by root t rate. So often you'll find people just saying 1 by root t, because the dependence on d really depends on the norms that you're talking about. And so if I'm verbally talking to you, I'm not going to sit and define infinity to something like that and put a root d. So I'll just like informally say, okay, like 1 by root t is the rate for convex functions. The dependence on dimension depends on the geometry. If you were going to write it down formally, you need to include it, but verbally people just say 1 by root t rate. So stochastic optimization, if I don't have strong convexity, 1 by root t is the best I can get. That's what this is saying. This is saying there exists an oracle and there exists a set such that for all algorithms, there exists a function such that my error is at least this much. Okay, I've tried to parse it in many different ways in English. Let me know if you have any questions about reading this in English. That's what you need to do.
Are the orders of the super names?
Yeah, they're really important because that's the order in which the players play. Yep. So you can't switch these two, for example. In fact, maybe that's a good point. Maybe you should appreciate that you can't switch these two, and I'm going to make a kind of I'm going to make a claim, and then you can see why that claim is true. Okay, inf over a. So you get to start at whatever point you want, right? So that's the good part. So you get to start at whatever point you want, and after that, use gradient information. Okay, so the expected function error is 0. So this is what I'm claiming. I'm claiming that if you switch the sup and the inf, that the value is just 0. And can anyone offer an intuitive explanation why?
Yeah.
Sorry, can you explain that in a little detail?
I mean, you know f, so you can like solve it without asking the oracle.
So you know f, so you can solve it without asking the oracle. Yeah, that's exactly the reason. That is, if I gave you a worst case, for any particular f, there is always an algorithm that solves it in 0 steps. It just starts at the minimum and then does nothing. Okay, so for any given f, there is an algorithm that solves it. For a different f, there's a different algorithm that solves it. But what I want to claim is that, like for any given f, so basically for f1, there is an algorithm a1 that takes 0 steps. And for f2, there is an algorithm a2 that takes 0 steps. But the point is that that algorithm a1 might take 0 steps for f1, but in this class, there is some other function on which it will take 1 by root t steps. Okay, so definitely any algorithm that starts from x0 has already minimized the function if the function happened to have its minimum at x0. But that's not the claim. The claim is that there is no single algorithm that can do well for all functions. Definitely there is a single algorithm that can do well on a particular function, but there is some other function in your class on which it does terribly. Not terribly, but as bad as that. We have some feel of why you can't switch these two and what the claim is saying.
Can you say again what's the first two sub?
Oracle. So what's the oracle? I get to add normal noise or Laplace noise or something like that. So Dumbledore first chooses an oracle by which he's going to return like queries to you. So you ask a query and he returns that query with the function value and the gradient value with some added noise of some fashion. So he chooses an oracle. Then he chooses a set. He tells you, okay, I'm going to optimize over some set like the L2 ball or something like that.
Only first order oracle, right?
Yeah, it's a first order oracle. And so that's why I said it's like an oracle that returns first order stochastic oracle, first order stochastic oracle. Then he chooses a set and he tells you you're going to optimize over this set. And you choose an algorithm that says, okay, this is my algorithm. It could be gradient descent, for example. And then he says, okay, I'm going to show you that on this function, the algorithm that you chose, he's going to pick a function which is the worst case function. He's going to show you on that function that you're going to suffer an error of at least 1 by root t after t steps.
So the only condition for the Oracle class is being unbiased.
Unbiased and bounded variance.
Okay, yeah.
Okay, so that's a technical condition I've included in my notes. I can't add infinite variance noise,
Yeah.
in which case you're seeing noise. So it just has to be bounded variance, which is kind of natural. Any questions? It's important to be able to parse these things. Okay. Oh, maybe I'll just leave this here and go there again. Okay. Okay, let's look at some more examples which are definitely important. Okay. So that was a stochastic oracle and stochastic optimization where you get noisy function values. How well can you do if there was no noise in your function and gradient values? So you were calculating the exact function gradient value at every step. How well can you do? Okay, so this example is from Nesterov, and he has these. I've written it in the notes. It's called Introductory Lectures on Convex Optimization. It's a book, and this is from there. Okay, and the short note is that smoothness and non-stochasticity, they buy you a lot. Okay, so if your function is smooth, for example, it's not the hinge loss, it's the logistic loss or something like that, and if you're non-stochastic, that is, you actually get exact gradients at every step, then you can get way faster rates. Okay, so let's see what the statement looks like. So I'm going to make two statements, and they're going to be off that form, but I'm going to try and not write down that entire thing. I'm going to say it a little more concisely. P x naught d2 L2. Okay, so this is a class of functions which is like, say you're starting at x naught, so x naught is some starting point, and you're guaranteed that x naught minus x star is at most d2. Okay, so this is the 2 norm bound. So, okay, this is the class of functions which is L2 Lipschitz. So it's Lipschitz in the 2 norm, and it's non-smooth, and it had your set is of bounded diameter. It's the L2 ball around x naught of diameter d2. So that's the set. Okay, so if you're dealing with this class of functions, then the lower bound for deterministic optimization f of x star is at least L2 d2 by 1 plus root e minus 1. Oops, this should be d. Okay.
So you say L2 is the function itself, not the gradient.
Yep. This is the function is Lipschitz, not its gradient. So it's non-smooth. Okay. So its gradient is not smooth. Its gradient is not Lipschitz or anything like that. It's non-smooth, and the function is Lipschitz, right? So suppose this is that class of functions. So it's just non-smooth optimization basically. So this is just non-smooth deterministic optimization. What I showed you there was non-smooth stochastic optimization. This is deterministic optimization, and what you see essentially, if you basically ignore the dimension dependence and this constant 1, is you get a 1 by root t rate in this setting also. Okay, so I took away stochasticity. Okay, I gave you exact gradient, I gave you exact subgradients of function values, but you still cannot do better than 1 by root t. Okay, so this is a deterministic lower bound. I'm giving you like noiseless subgradient values, and you can still not do better than 1 by root t. And so for both of these, the algorithm that achieves it is subgradient descent. Like you should have seen it in the other optimization course, but basically SGD gets you a rate of 1 by root t, and you might ask yourself, is this optimum? SGD sometimes stands for subgradient descent and sometimes for stochastic gradient descent, and both of them achieve a rate of 1 by root t. So if it's subgradient descent, you have noiseless subgradients, and you just take a step in the direction of the subgradient at every step, you're going to get 1 by root t. If it's stochastic gradient descent, you basically have stochastic gradients, and you take a step in the direction of stochastic gradients, and you get a rate of 1 by root t. So I think earlier, Abhimanyu, who isn't here now, had earlier asked in one of the earlier lectures, this 1 by root t, is it optimal? And the answer is yes. If you don't have anything like strong convexity, and your function is non-smooth, then you can't do better than 1 by root t. Okay, so 1 by root t is the rate to expect. But suppose your function is now smooth, okay, and when it's smooth now, it's differentiable is what I mean. If it's smooth, meaning it's differentiable, and its gradient is Lipschitz, okay, so it's gradient f of y is at most L times x minus y. So if you want, just put 2 norms. I'm just going to assume it's 2 norm for the moment. Okay, so it's the gradient is L Lipschitz, and say the squared loss would satisfy something like this. Then, and that's my class of functions now. It's the same thing, except that this L is going to mean the Lipschitz constant of the gradient. Then the same function error ends up looking like greater than equal to 3L x naught minus x star squared by t plus 1 the whole squared. Okay, so maybe this you should just think of this as d squared. Okay, so it looks like 3L d squared, that's fine, that's some dependence, divided by t squared. Okay, so basically I just gave you smoothness, I just made it differentiable, and your rate went from 1 by root t to 1 by t squared. Okay, so this is basically what smoothness buys you. Okay, both actually, non-stochasticity plus smoothness, that's what it buys you. This is 1 by t squared. And I think this was kind of very important, and I'll come back to that later, why like this lower bound led to an entire new class of methods. Just like the fact that the lower bound was 1 by t squared led to a new class of algorithms. And before that, I'll give you one more example, and that's for strongly convex functions. Let's finally get to strongly convex functions. Okay, so that's an example. Let's get to one more, and this is strong convexity, and I think I defined strong convexity somewhere earlier, right? Was it here or was it here? Oh, it's here. Okay, so this is what you mean by strong convexity. Another way to define strong convexity is to say that the smallest eigenvalue of the Hessian is at least lambda, this guy, okay, maybe sigma min if you want. So the smallest eigenvalue of the Hessian is at least lambda. That's what this is saying. And what you mean by this smoothness is that the largest eigenvalue of the Hessian is at most L. That's what the gradient being Lipschitz is saying. So these are all things you should know from the other class. But if yeah.
Does that definition apply to the L2 norm?
Yeah, this is for the L2 norm, but kind of in spirit applies to other norms also up to a dimension factor. Yeah. Right. So if a function is strongly convex and non-smooth, okay. So if a function is strongly convex and non-smooth, and say you get stochastic gradients, okay, and stochastic gradients, then the function error, I'm going to just call that epsilon f, the minimax function error, these are lower bounds, right? So the minimax function error is at least L squared by lambda squared t. Okay. So if it's, so this setting was non-smooth and stochastic gradients and convex. This is non-smooth and stochastic gradients and strongly convex. That's the only thing I changed between these two settings. Okay, and the rate went from 1 by root t to 1 by t. Okay, the dependence on this is also important. So this is often ignored. This is called the condition number of your optimization algorithm, of the function, and that's the ratio of the largest and the smallest eigenvalues of the Hessian, and that's just L by lambda. And so it really matters what the dependence of the condition number is for these algorithms. So it turns out that you can prove a lower bound like L square by lambda square t. So the error rate is 1 by t. Now, as I said earlier, that smoothness and strong convexity buys you a lot. And so my last example is, suppose it's strongly convex and smooth, and you get non-stochastic gradients. So that's you get actual deterministic gradients. Okay. Then what you get is that, let me try and can I push that up? Okay, you get epsilon f is greater than equal to lambda by 2 times root k minus 1 by root k plus 1 the whole to the 2t times x0 minus x star squared. Okay, so k is what I'm calling the condition number. That's called kappa usually. It's the ratio of L by lambda. That's what kappa is. And when you have strong convexity and smoothness and deterministic gradients, you get an exponential rate. Okay, so you get some constant, which is root k minus 1 by root k plus 1, where this is k, the whole to the 2t. Another way to write this is e to the minus some constant times 2t. Okay, so this is an exponential rate, right? It's not polynomial with t, it's exponential in t, right? And multiplied by a constant. So when you go from non-smoothness to smoothness and stochastic to non-stochastic, you go from a 1 by t rate to basically an e to the minus t rate. It's a huge jump. This is exponentially faster, right? And again over here, the fact that this is root k minus 1 and root k plus 1 really matters. So why does it matter? It turns out that somewhere in the 1980s, Nesterov was studying these methods, and gradient descent was really popular. So he analyzed gradient descent in, say, this setting in which it's smooth and non-stochastic, but it's not strongly convex, and he got a rate of 1 by t. Okay, so this is gradient descent, he got 1 by t, and he proved a lower bound of 1 by t squared. And then he came here and he took the strongly convex and smooth setting with non-stochastic gradients, and he proved that gradient descent gets a rate of k minus 1 by k plus 1 to the 2t, the same thing basically, times some, say, the diameter squared. Okay, so he got so over here he got root k minus 1, root k plus 1, he got k minus 1, k plus 1. Just remember that this k can actually be huge. It can actually be as large as n squared. I'll tell you why later on. If n is your number of points, for example, that you're optimizing over, then your condition number can be absolutely massive. It can be like in the millions, and I'll tell you why later. But basically the dependence on this condition number is absolutely crucial. And he found that gradient descent was k minus 1 by k plus 1, but he was able to prove a lower bound which had root k. And similarly over here, he was able to prove 1 by t for gradient descent, and he got 1 by t squared as his lower bound. And so then he realized that, okay, there's a gap. Could be that his lower bounds are loose, but it could be that his upper bounds are loose. And then he invented accelerated gradient descent somewhere in the 1984 or something like that, precisely because he saw this gap. He said, look, I'm looking at the lower bounds and I'm not finding them to be matching. And he suspected that the fault was in the upper bounds. And he invented accelerated gradient descent to get this rate and to get this rate. So basically, accelerated gradient descent is optimal. If any of you ever use gradient descent, stop using it. You should never use gradient descent. You should always use accelerated gradient descent. There is no reason to use gradient descent.
What about, in practice, do you?
Yeah, in practice, there's a huge difference between like at least like all the homework exercises we give and every time I've tested it, there's a huge difference between the two.
Do you think that's always the case? That if you have a theoretically better bound, you should use the algorithm that achieves that as opposed to?
Well, with accelerated gradient descent, yes. It's not always the case. So accelerated gradient descent, so I can tell you a little bit something interesting about accelerated gradient descent. It suffers from what's called Nesterov ripples. And Nesterov ripples are if you actually drew the convergence of the function over time, then it'll end up looking something like that. Okay, and he comments about this and he says that this is not a descent method. Okay, so what I mean by a descent method is that f at xt plus 1 is always less than f at xt. Okay, gradient descent is a descent method, so it does actually decrease at every time step, but this does not. It has these bumps that sometimes it'll do worse and then do better, it'll do worse and then do better, and so on. And he actually comments on this and says that this is a globally optimal rate, and looking for descent, trying to find algorithms that achieve descent is looking too closely. It's looking at too fine a scale, trying to make sure that at every step you're making progress. And instead, if you look at a global scale, you don't care about whether at every step you're making progress or not, as long as overall you're doing well. And he says that, so basically, he made the claim, I think long ago, that every optimization algorithm is not going to be a descent algorithm. Okay, so he made that claim, and basically I think he has lived up to that claim more or less. Subgradient method is not a descent method. Accelerated gradient descent is not a descent method, and they all suffer, subgradient descent as well as accelerated gradient descent suffer from these kind of ripples, but they're optimal. And he made the claim that pretty much if you're proving descent at every step, you're proving too much and your algorithm is very strong locally and very weak globally.
So is there any intuition for where it's going when it's not descending?
There is, but I can't get into it right now. Acceleration would take me an entire class, and I have very interesting things to say about it, but this is not the place. This is upper bounds really. But maybe this should add some significance to why lower bounds are important, because it is only when Nesterov realized that there's this gap between what gradient descent observed and what he could prove as a lower bound that he said, okay, let me try and find another method and design a method that's optimal, that he designed this. Okay. Now, there are, in the last 10 minutes, maybe I'm going to talk about exceptions in some sense to these upper bounds. And maybe this is maybe the most important part, which is when you should not listen to these upper bounds, right? If you have not absorbed all the upper bounds right now, that's fine. Go back and look at it and you'll broadly get it, okay? And I can summarize it verbally right now, is that if it's non-smooth, whether it's deterministic or not, you're going to get a 1 by root t rate. If it's smooth, but it's stochastic gradients, you'll get a 1 by t rate. If it's smooth, but it's deterministic gradients, you'll get a 1 by t squared rate for convex functions and an exponentially fast rate for strongly convex functions. Sure, yep.
Were you planning to say anything about the second order rates? Because I think a lot of this, depends on the condition number. I don't remember exactly, but that kind of goes away. And there's a gap between the accelerated methods and the true second order.
Yeah, so I wasn't planning to say much about second order methods, but yeah,
okay,
maybe.
Just curious.
Yeah, sure.
I think it's an interesting.
Yeah, definitely second order methods are interesting too, but I think just absorbing first order methods itself takes a little bit. So I think zeroth and second also makes sense, but I think I just wanted to focus on first for one class.
Yeah.
Oh, maybe I shouldn't rub this. Maybe I should rub this. Okay. So maybe the most important exceptions to these lower bound rules are exactly the first algorithm that I introduced. Okay. So it's this loss function. Okay. So very often in machine learning, we're actually trying to minimize something like this, which is a sum of loss functions, right? I'm going to assume that, let's say that these are smooth and strongly convex, okay? Now, as I just told you, if they're, what do the lower bounds say? Okay, so you have two methods of solving this. One method is deterministic, which is at every step, I'm going to go through all my data and calculate the exact gradient. Okay, that's the deterministic. And if it's smooth and strongly convex, then the deterministic thing will get you an exponentially fast rate. Okay, so that was this statement. If it's strongly convex and smooth and deterministic, then I'm going to get an exponentially fast rate. Okay, now this is smooth and strongly convex. Now if it's stochastic, okay, so if it's so by stochastic, again, I meant that you pick one random data point at every step, calculate the gradient at that data point, take a step, and so on. Okay, so it would be WT plus 1 is WT plus a step size times gradient of Li at WT. Okay, and this one would be WT plus 1 is WT plus eta times sum over I equal to 1 to n of gradient of Li at WT. Okay, and then the lower bound says that this should get you a rate of 1 by t. It's strongly convex, but I have stochastic gradients, and this is the best I can do with stochastic gradients. Now, in some sense, why I'm going to tell you an exception to these lower bounds is because the lower bounds hold for general classes of functions. So if I have a general function, then I can't hope to do any better than 1 by t. But this function has a specific form, which is it is an average of loss functions. Okay, so it's not just some f, it's not just some black box f, it's specifically an average of loss functions. And there is structure to this problem that turns out that you can exploit that structure. Okay, and this was just 2 years ago, I think 2012, that there was a paper by Schmidt, Lahu, and Bach. Okay, and they have an algorithm called SAG. So you can check out this paper later on. So this algorithm is called SAG for stochastic averaged gradient, and it turns out that they're able to make only stochastic updates. It's not an update of this form. I'm not going to describe the algorithm to you, but it's very simple. It maintains a list of gradients, okay, one at each data point. Okay, so it maintains a list of gradients from, and at each step it takes one of these and updates them, and takes a step in terms of the average. In the next step, it takes another one of these and updates them, and then takes a step in terms of the average. I'm not going to describe the exact algorithm to you now, but at every step, it calculates only one gradient. Okay, so it looks very much like a stochastic method, but it gets exponentially fast rates for, even though at every step it's actually only calculating one of these, then it does some update and adds something else, but it gets exponentially fast rates for this algorithm. And this is the algorithm that I think, Nicole's not here, but she told me that this saved her 18 hours on her experiments, because she was running accelerated gradient descent, I don't know, something like that, and which goes through the entire data set at every step to calculate a gradient and gets you an exponential rate. But instead, if you ran SAG, which basically takes one gradient at every step and gets you an exponential rate, and so it turns out in practice it saved her a huge amount of time. So, but this is it sounds like an exception. It sounds like, wow, you're doing only one of these at every step. How are you beating 1 by t? Well, I'm really using structure. I'm using the fact that it has this particular form that we often need, right? And the other maybe classical, now classical, it's probably just 10 years old. The other classical setting in which the lower bounds don't really reveal the truth is when you're trying to oops, you're trying to minimize f of x plus h of x, where f is nice, so f is smooth. It could be strongly convex or not. And h of x has some nice form, and that form is that you can calculate a prox function for it. But just for example's sake, let's just say that this is the L1 norm, like the lasso or something like that. Then the lower bounds would say that this function that I'm minimizing is non-smooth. That's it. It has a non-smooth term. The function is non-smooth. I cannot do better than 1 by root t, whether I calculated exact gradients, not exact. Whatever I do, I can't do better than 1 by root t. It's non-smooth. But it turns out that proximal, so accelerated proximal gradient descent can use the fact that this is exactly f of x plus h of x. This is smooth and that is non-smooth. That is you can split out the non-smooth part and do something on the smooth part. So in some sense, what you can do is you can do your accelerated gradient descent on this part, and you can do some kind of a proc step on that part. So because it's the separable form, and you have a prox function for that, which turns out to be some soft thresholding, that this can actually get you either 1 by t squared rates if it's convex, or it can get you exponentially fast rates if it's strongly convex, right? But the lower bounds would say 1 by root t. But the lower bounds hold for a general class of non-smooth functions. If I give you a special non-smooth function with some structure, then yes, then you can possibly exploit that structure and get better algorithms. And I think maybe that's what you should be looking for. I mean, if ever you come across a problem, first thing would be, okay, what would the lower bounds tell me in this setting, and what is the optimal algorithm? And then can I exploit something special about what I'm dealing with, which is often the case. You're often dealing with something like this, or you're dealing with something like this, and then you can actually do better. But even then, you can actually, like, it turns out that first proximal gradient descent was invented by Beck and Teboul, and then years later, accelerated proximal gradient, because it's hard to get the proofs to work. So the accelerated algorithm came much later. But initially itself, when they invented proximal gradient descent, they could have asked themselves the question, is 1 by t the best we can do? So they got 1 by t. And it turns out, no, you could accelerate that too and get 1 by t squared. And so that was all in the mid-2000s. So pretty much at every point, new algorithms have been formed by people asking the question, okay, is this the best I can do for what I have at hand? And then being like, probably not, and finding something better to do. Any questions? Okay, that's basically all I had for today. If you have any questions, feel free to ask. Otherwise, I'm kind of done. Okay, thank you.